Alright, so I noticed that a lot of people had trouble with one of the homework problems from chapter 2, so I thought I'd make a little video and show how you would complete that problem. So the problem was number 29.97, and the problem is about the student who is trying to catch a school bus. So I wanted to write down the information that I was given. Your numbers were probably a little bit different, but that shouldn't affect your ability to follow along and to see how we do this. So it says that our student has a top speed of 5.3 meters per second. And what's implied but not directly stated is this is the speed that she's going to be traveling at, so she does not have any acceleration. I'm also going to say that her initial position is 0. What I'm trying to do right here is I'm trying to write down the information that we're given in the problem. And I'm going to explain with a picture why I chose to make her initial position 0 in just a minute. But I also wanted to talk about the bus and do the same thing for the bus. So the bus, I'm going to say its initial position is 38.8 meters. And the reason that I say this is the distance that the student was away from the bus when she started to run and when she was running and when the bus started to pull away. So in the problem, I think it says the bus is 38.8 meters away from the student when it starts to accelerate. It's it's starting from rest, so the idea is that the student's running to the bus, which is stopped, but at the instant that the bus starts to pull away, which is when it's accelerating, which for me was a rate of 0.176 meters per second squared, at that instant the bus is at 38.8 meters. So the basic idea here is that we're going to be using these expressions that we saw in this chapter, which are the expressions for position and velocity in the case where we have constant acceleration. And so I'm going to use these equations, but I'm going to make them specific so that I'm going to be able to write them for both the student and the bus in a minute. But first I wanted to sort of draw a picture. And this is something I would recommend that you do as well when you're doing problems. Pictures always help to visualize what's going on. So here's my bus. Looks like a truck, but you know, if I was a good artist, maybe I wouldn't teach physics. So the idea is that she's running with a speed of 5.3 meters per second. The bus is accelerating with a rate of 0.0176 meters per second squared. And now I think it makes sense that I said this is x equals 0, so this is where the person is, the girl, and then this is where the bus is. And that's the 38.8 meters. And so we can sort of see that when we start the whole scenario, the initial position of the student is 0 and the initial position of the bus is 38.8. So I'm going to, again, I said I'm using these expressions, and I want to sort of tailor them for the student and the bus. And so I'm going to write the student expression over here, and I'm using some subscripts. I know sometimes you're not crazy about these subscripts, so I'm just going to sort of add the subscript of s to the equation that I wrote up here, just to sort of emphasize that the values I'm using are for the student. And so for the student, her initial position was 0. Oops, I forgot a t. Her initial velocity is 5.3, and she didn't have any acceleration. So the expression for her position is 5.3 t. And so that would allow us, if we put in any value for t, we would get the value or the position of where the student is at that time. I'm going to do the similar thing for the bus, again using my subscripts, just to emphasize that these values are specifically for the bus. Not using the subscripts can make things confusing, because then you start getting confused. Is this the X for the student or the X for the bus? So I think it's a good idea to use the subscripts. So the initial position of the bus is 38.8. It has a 0 initial velocity, so that middle term is 0. And then I do 1/2 the 0.176 times t squared. So the final expression that tells us where the bus is at any time looks like this. And so the question is, you know, I want to know when the student's going to catch the bus. And so we have to ask ourselves how we're going to use these expressions to help us. And what I would realize is when the student catches the bus, they are at the same place. And what this means is that the position of the student is equal to the position of the bus. So we would make 5.3t equal to 38.8 plus 1/2 0.176 t squared. And so this is the equation that we have to solve. This is going to allow us to find the time when she's going to reach the bus. So now math problem, more or less. So saying that her position is equal to that of the bus, I got 5.3t is equal to 38.8 plus 1/2 0.176 t squared. Now I'm going to just kind of make it look a little nicer so that I can solve it. I'm going to take the 5.3 over there. If I take half of the acceleration, it's 0.088 plus, oops, this is a minus 5.3t plus 38.8. And so this is a quadratic. It's quadratic in time. And so you should know how to use the quadratic equation to solve for t. If you don't, you need to review this. So it's negative b, which is the coefficient of the time. So it's 5.3 plus or minus the square root of b squared, which is minus 5.3 squared, minus 4ac. And all that is over 2a, which is the 0.176, if I multiply the 0.088 by 2. And so I'm going to eventually get down to, when I do some simplification, I get 5.3 plus or minus 3.799 over 0.176. Notice I'm keeping a couple extra significant figures as I'm doing my calculations. If we round off constantly in our intermediate steps, this introduces error, which gradually builds up and can actually end up giving us an incorrect answer because it's too far off from the correct one to be considered correct. So I solved this problem. We talked about this a little bit in class the other day, where I get two possible answers. But this is really, it's just the math is telling me when she could catch the bus. But I only want it, the first time is quite adequate because once she catches it, she catches it. So I'm going to use the 8.53. And so then if I see this is my first answer, and then when I see how far does she run to catch the bus, which is the second question, well, her position is given by 5.3 times the time, so I put 5.3 times the 8.53, and I'd see that she's going to run 45.2 meters. how fast is the bus traveling when she catches it. Well, now this is a velocity problem or a question, so I'm going to go to my general form for velocity with constant acceleration and then put in my values for the bus. The bus, remember, had an initial velocity of 0 and an acceleration of 0.176. So the velocity of the bus can just be given as 0.176 times time. So I find how fast she's going. The bus is going at that time when she catches it, which was 8.53. And I find that it's going 1.5 meters per second. Finally, the last question asks, what if the velocity of the student is 2.8 meters per second? Will she catch it? Will she catch the bus? Well, basically, I'm still going to find the time when her position is equal to the bus's position, and answering the question, will she be able to catch it, will depend on whether I can find a time when this is true. Keeping in mind, the position of the bus isn't going to change because the expression for it isn't going to change because we've not done anything to change the motion of the bus. So the position of the bus is still this, but by changing her speed, it changes her expression for the student to 2.8 times t, because this is her initial velocity. So those are the two terms I'm going to set equal to each other. So when I say the student position is the same as the bus, I get 2.8t is equal to 38.8 plus 1/2 times 0.176 t squared. And if I rearrange this again, and solve for t, you see that we run into a problem when we're trying to simplify for t, because this is going to be a negative number, and I can't take the square root of a negative number isn't real, and so the answer is there's no real time when they're going to be at the same position. And what this means is that she can't catch the bus. All right, so hopefully you find that helpful. Play it as many times as you want, and try it with your numbers to see if you can do it on your own.